Hey guys, you're on A-Level Maths with Daniel Dallas. Today I'm going to show you what binomial expansion is, how it works, and how to use Pascal's triangle as the shortcut and fast track in order to calculate the expanded way or the expansion for binomial. Of course, this has some limitations. I'll also give you an idea when it's highly recommended to use instead of like calculating those binomial coefficients, even if you have calculator. So sometimes much faster to use Pascal's triangle. All right, so if you're ready, let's get started. So here we just need to know what binomial is. So binomial means two, so that's why you need to have two terms, a and b. It might be like more complicated structure like 2x squared, for example, and plus 3, let's say, y in any power. So that might stay instead of a and b. And this raised to the power n, for example, this structure may be raised in the power, let's say, 3. Of course, for the power 1, for power 2, you might use alternative formula, right? Let's just remember, if we use a and b squared, we just simply need to multiply the structure a plus b itself, okay? So that's what you can do. Or you can use the formula as the shortcut. So if you calculate, not calculate, but apply the formula, you'll get a squared to a b and b squared. But this is as a result of expansion. But of course, for a cubic one and even power more than 3, it's much better to know the rule and the general idea how each term appears in those expansion like this, okay? And that's why I try to share the idea how it works right now. By the way, I want to tell you that if you, and some examples, you might have probably, instead of, let's say, 2x squared and plus 3y, you might have something like 2x and, let's say, minus 3y. How to work in this case, let's say, power 3. So you can easily say that if we marked a as 2x and negative 3y, so we put, instead of b, negative 3y, so you can write as still a plus b to the power 3, because normally for binomial we use addition rule, okay? So that's why instead of b, we just simply put negative structure as negative 3y. And then, hence, you can still use the general formula for that. Okay, let's get started. So first, it's interesting to have an idea how binomial expansion might work for the powers like 0, 1, 2, and probably 3. So that might be probably you can get the logic or the idea how each term appears and which power. So that's the main practice that you need to actually do before you get to know the general formula. So just remember, we actually did this when we went through sequences. Sometimes it's highly recommended to play with specific numbers and see the rule, see the law that lays behind the scene. Okay, that's the same strategy. So first, let's try to understand what if we have binomial to the power 0. In this case, we definitely have 1, right? Because no matter what stays inside, any number, any, let's say, term in the power 0 will give you 1. Okay, so next part, if it's in power 1, we'll get a1 plus b to the power 1. Because power 1 means the same as just a plus b. So that's why we finally get a plus b. So what about a squared plus b squared? We'll get a squared plus 2ab and plus b squared. Okay. As you notice, we start from a1 and b1. So the maximum power that stays in binomial expression. So here it gets for each term. So on edges, it means there always be the terms that stays as binomial a and b in the maximum power. For example, here on edges, you notice that a squared and b squared stays in maximum power. Obviously, if you try to play with cube, the first and the last term, so I skipped for a while what stays in between, but you definitely know that on edges, again, there's going to be a and b to the maximum power. What also you might notice about how the formula of expansion might work. You start from the maximum power for the first term in binomial, which is a squared, and then you continuously or you permanently decrease the power of the first term. Indeed, that was a squared, now it's a to the power 1, and finally before b squared we can assume that it stays a to the power 0, right? So in this case we can assume the same. We don't know, we have no idea of coefficient, but we might assume that here is going to be decreasing power of the first term and simultaneously, according to the previous case, increasing power of the second term. So that's why here the next term is going to be a squared b, and probably the next term is going to be some coefficient we have no idea right now, but a is going to be staying in the power of 1, while b gets a rise in power by 1. Okay, so that's why it gets b squared, and finally we will have b cubed. So that's why that allows to make some idea of the general rule that valid for both binomial terms a and b. So you have the maximum power, for example, let's consider the cubic binomial. The maximum power for the first term a cubed, then decreasing power for the first term and simultaneously increasing power for the second term b. Okay, yes, we have some coefficient, but they arise as a result of simplification. So but at least we got the logic. So in here the final term, what stays before b cubed, is definitely there will be a to the power 0. Okay, and then goes b cubed. Okay, that idea allows us to generalize the formula for binomial in case if we have general power n. So we have power n, so that means we will have the maximum power for the first term, then there goes some coefficient, the power decrease every time by 1 for the first term in binomial, and simultaneously increasing by 1 for the second term b. So that's how you can get the logic for the following terms and the sequence. And the last term is going to be b to the maximum power n. So the idea now is how to properly figure out coefficient. Okay, but before we do that, you also notice that every time you can consider as summation of a to some power and b to some power, because even here, if there is actually no b staying nearby a to the power n, we can assume that they might be b to the power 0, as well as in the last term b to the power n, they should be a to the power 0 finally, because the power falling down for a from a to the power n up to a to the power 0. Okay, as well for b, it's rising from b0 that you might see here up to b to the maximum power of your binomial n. So that's the idea that lay behind your observations. Okay, so that's why before we're doing that, I'll show you how to use sigma notation. Instead of writing those expressions, we can rewrite using the following. Because we noticed from the previous observation the sort of A-B product, and we summate those products in different powers, we can generalize this idea and use the sigma notation. So sigma notation means simply the sum, okay? You trying to sum up the terms. So your typical term should look like a to the power some power and b to the some power, right? and we trying to sum up those terms. So that's why I put sigma notation, and I would say that we can sum up and running index, actually that you trying to sum up those terms. Let's say R, okay, and B, as you remember, B first it's appeared in the power of 0 and up to the power of n, so b to the power of n. So that's why we can say that if we set up R as the power, or yes, as the power for b in the index form, so we can put R, and R will be changing from 0, that's initial term, the first term, up to n, up to the maximum power, okay? So next, what about A? The power for A starts from A to the power of n, okay? It starts from n, and it's consequently decreasing up to A to the power 0 every time by 1. So that's why if you use running index as R, so that's why the power for A should look like as n minus R. And indeed, if you just try to use this formula, you plug how the formula actually works. For the first term, you need to use R equals 0, and if R equals 0, you'll get the following term, A to the power of n and b 0. That's okay, that's your first term, A to the power of n. If you plug next R equals 1, you'll get A to the power of n minus 1, and b will get 1 more. So that means, in comparison with the previous one, it will get 1, okay? And up to, let's say for R equals n, because that's the final, we'll get A to the power n minus n, which will give us 0, right? And b will get the maximum power R equals n, that will correspond to the last term, okay? That's how sigma notation works. So make sure you understand. However, here, that's going to be some coefficients. We have no idea, but we understand that they might be specific rule for coefficient. If you try to expand a plus b to the power 4, probably you'll have something interesting, like probably 4 appears as the coefficient and 6 appears as the coefficients. So that's why it means the coefficient every time will have specific form. And actually, if just I'm going a little bit forward, and I'll use their combination coefficients from statistics. So, and choose R, actually, or, you can use this notation. So that will stay in the formula, and R. But right now, I'm going to show you how to calculate those coefficients without using actually the formula, because if you grab the formula from statistics, you'll get that this combination coefficient for a combination, so you take an R from n, so that means when the order of choosing doesn't matter. Just remember a little bit, statistics and order doesn't matter in this case. So that means you'll use exactly this formula, n minus r factorial and times r factorial. So that what stays for C, and choose R. And those coefficients, of course, can be calculated, but it's quite daunting, Sometimes you don't need to do that, especially if you have not quite big powers, like up to 5 or even up to 6 or 7. It's much better to use Pascal's triangle. And that means right now we are going to make some observations, okay? So try to understand that we actually generalize the formula using sigma notations. However, so it's, sometimes if you ask, you need actually to use this formula. But if you're not asked, so you can skip and just consider general formula with using plus and dots, okay? So that's an idea. And now we're gonna go to Pascal's triangle and try to see how the Pascal's triangle works. So let's consider the following binomial expressions. So we know that a plus b is simply 1. A plus b is going to be a plus b, right? And here is going to be a squared plus 2ab and plus b squared. That's what we know. And if we use specific triangle that actually responsible for coefficients before those terms, that you can actually enumerate like the first term, the second term, and the third term. So you can actually try to correspond those binomial expansions for each, for each step in this pyramid or in this triangle, because this is actually looks like triangle completed or made of numbers. Okay, so that means what you can say that this corresponds to n equals 0 when the power n is 0. We remember that we can use general structure, right? So this level will correspond to 1, that level will correspond to 2, and so on. And those numbers, if you just have an expansion here, a squared plus 2ab plus b becomes coefficient before each term. For example, this one is the coefficient before the leading term, or the first term, a to the power 2. So this 2 here is the coefficient before the mixed product a and b, so that's the second term. And the last is going to be the last coefficient. So every time those actually numbers shows you coefficients, that how you can get. But the question is how we can arrange those triangles, okay? So now we can definitely, on this slide, you can see that now we can use Pascal's triangle in order to get those coefficients for binomial expansion with a specific power, right? So let's assume we have the power a plus b to the power 4. So that's why we count, and that's 0, that's 1, that's 2, that's 3, that's 4. So that's why for a plus b to the power 4, we are going to use this row that gives us coefficient 1 before the first term, 4 before the second one, 6 in the middle, and 4 and 1 corresponding to previous and like previous term and the last term. Okay, so that means using this triangle we can actually arrange those expansion using those coefficients. For example, let's take a to the power 4 with coefficient 1. On top of that, we add 4, yes? And as you remember the formula, that power for a is decreasing by 1. So that's why we'll use power 3, while power of b is increasing by 1. So that's why a cubed b. The next is 6. So that's why we add 6, a squared, okay? And b squared. And again, 4, so we add up on top of that, we add in 4 times a power is still decreasing, so a to the power 1. So but I missed out, I'm not going to write this power, and b still rising, so b is cubed. And the last coefficient 1 is the coefficient before the last term, which is b to the power 4. So that's why obviously this triangle will help us to figure out coefficient for any row. But let's say the complexity. So if you count 5, 6, 7, and let's say 8 and 9. So using power of 9, that's pretty hard. When power becomes greater, it's harder to use those coefficients. However, if you're given this triangle, you can use as, ready to apply instrument, ready to apply tool, okay? So that's why if you have this triangle, or at least you can understand how the next, let's say, how the next blocks, if it goes from top to the bottom, right? And if you can get the idea how the next block and how the numbers appears in those blocks can be figured out, so there is no problem even up to the power, I think, 8 and 9. Okay, let's have a little practice. How I want to show you how the idea of Pascal's triangles and how the numbers can be calculated. Let's have a look here. So what we have the following. We have 1 on top, and if you put this arrow as, lateral diagonal, you'll have always ones, okay? As well as here, so on the right side. So that's why if you construct those triangles from scratch, it means that you need to start from the top level, right? Which in this case is 1, definitely. And all lateral sides, according to the levels, will be everywhere ones. So here is for binomial expansion is going to be 0 level. That's level 1. That's level 2. That's level 3. Okay. And even we can take level 4. My idea is to get there, to get the principle of how numbers, of how you can calculate numbers below. Now, let's go next, and it's good to know how you can get the middle term. So, numbers that stays below. At every time, if you notice, if you take the 2 exactly above your number 2, that means you need to add those 2 numbers above the number that you want to calculate, and that's how you can get the number below. So that means in order to get 2, you just simply need to add 2 adjacent number above. Okay, let's see how those 3 can be calculated. So again, you take in the lateral one, it's always 1, right? The edge number, and those 2. You add them up, 1 and 2, you'll get 3. So the same, you can get 3 here in the same way. Let's go to level 4, when the power is 4. So that's the same. You take in the lateral number, and you add in 3 that stays nearby together, and they are above those 4. So that's why 1 and 3 you can get 4. 3 and 3 you'll get the middle term, which is 6 in this case, and again 3 and 1, that's how we can get 4. Let's take any random block. For example, let's take this 6 and let's take that's 15. So together 6 and 15 will give you 21, obviously. Let's take 1 and 6, that will give you 7. No matter where you are, right, you can definitely get the idea that in order to get the number below 2 of other 2 numbers, so for example 35 and 21, and you want to calculate number below, you just need to add them up, okay? And make sure you remember that on the lateral side everywhere there goes 1, okay? So let's try to have a little practice, yeah? So construct Pascal triangle for the following binomial. Let's try to work it out. It's pretty easy, okay? So construct the, this is level 4, so that's why I just mark 1, 2, oops, sorry, level 0, 1, 2, 3, and 4. That's our target level. So right there, okay? It goes up to here. And let's fill the table. So 1 everywhere. 1, 1, 1, 1. So we add in those 2 ones and we'll get 2. Then we add 1 and 2, and again 1 and 2 and 1. And here the target level will get 4, 6, and 4. So that's why we've got all the coefficients. You see that it doesn't take a lot. Instead of if you do expansion manually, like x plus 4 times itself, and that's 4 times in a row. So that's why we've got everything. And now just simply I write the structure. So x plus y to the power 4 will get the following terms, mixed terms. So x will get coefficient 1. So that's why it's going to be in the maximum power. Then goes coefficient 4 with x cubed y. Then goes coefficient 6 with x squared and y squared, and then goes coefficient again, this 4 with x and y cubed, and the last one is going to be 1. That means it's going to be it's going to be y to the maximum power y4. Okay, so that's how you can use this triangle. That's how you can construct easily, and even up to, let's say, a level 8 or 9. That's pretty simple to construct, okay? Just make sure you can do that, practice for different binomial expressions, and in the next video, I'll just provide several problems as a revision for you guys in order to, get to know exam styles questions for A-level. That was pure maths 1. That's new syllabus 2020. So make sure you tuned up, you stay updated, and don't forget to visit A-level Zillion's class. I'm aware that currently he has binomial expansion for fractional powers. So I'll just set up several videos for this topic soon. But first, I want to make sure you got those basics. Okay, that was Daniel Dallas. Staying tuned up, and if you're new here, don't forget to subscribe and smash those bell button to be notified about daily videos. And if you have specific questions, just share them in comments. I'll always give feedback. See you later.